Welcome to another statistics seminar. So today we have Subhashis Ghoshal from North Carolina State University giving us a talk. I'll just step away because it kind of feels weird. Okay, so a little bit of an intro about our speaker. So Subhashis is a Goodnight Distinguished Professor of Statistics at the Department of Statistics of North Carolina State University. His research interests include Bayesian nonparametrics, high-dimensional statistics, graphical models, shape-restricted inference, differential equation models, etc. His research has been supported by grants from the National Science Foundation, including its Career Award, Army Research Office, National Security Agency, Samsung Electronics, etc., and several European agencies. He advised more than 30 PhD students and is a fellow of IMS, ISA, and ISB, ASA, and ISB. His book, Fundamentals of Nonparametric Bayesian Inference with Ad van der Vaart, won in 2019 the prestigious De Groot Prize for the best book in statistical sciences. He also held honorary positions chair professor in the Netherlands. He's currently serving or has served on the editorial boards of many top statistical journals, including the Annals of Statistics, and he is presently the president of the International Indian Statistical Association. Thank you so much for coming, and we look forward to hearing your thoughts. Let's welcome our speaker. So, sorry, one more thing. If you have a question and you're here in the audience, please raise your hand and we'll call on you. If you're on Zoom and you have a question, we have around 20 for now, and more coming people on Zoom. Please also raise your question or write your question in the chat. Thank you.
Thank you very much for your kind introduction and the invitation to give a talk here. It's a great pleasure. It's a nice campus to visit. And so I would give a talk on coverage of Bayesian credible intervals. So that's sort of an interesting aspect of like reconciliation between Bayesian and Frequentist, and sort of holy grail type results that we are looking for to justify credible intervals from the Frequentist measures. And this would be under a situation where we have a shape restriction on functions, and in this context, monotonicity for multivariate predictors. So this is a joint work with my current student, Kang Wang. And interestingly, Kang just visited Seattle yesterday. I didn't know that. I mean, he's being interviewed for a postdoc position at Fred Hutchinson. I knew that they are going to interview him, and I didn't know that it was going to happen yesterday. So I just learned today that he visited, and I think he's on his way back now, or maybe just reached Raleigh. And actually, this started with another student who graduated a few years back. So with her, it was like univariate situation, and now we are doing the multivariate one. So this work has been funded by a grant from NSF. So acknowledge that. So the situation is we have a regression model. So Y is the response variable, depends on some predictor X, and then error epsilon is the error. So to start with, say X is univariate and F is a function. Now, in common context, the natural, most often people use this kind of model under either linearity, and if it's beyond linearity, assume some kind of smoothness on F, and then they do smoothing to estimate the function. But there is a parallel to that. Instead of smoothness assumption, you can have structural assumptions like function is increasing. And there are other variants of shape restriction like convexity, etc. But yeah, let's, for this context, let's look at F, a function that is increasing. And this is an alternative to smoothing. So increasing puts a regularity condition that controls the complexity of the parameter space. So just like smoothing does, but it's a different way of doing that. So the thing that is known under this isotonic regression. There are algorithms for fitting this regression under this assumption of monotonicity. For example, the PAVA algorithm finds the least square estimator. The related problem, there is a univariate density, which is decreasing. Then the maximum likelihood estimator was characterized by Grenander as the left derivative of the least concave measurement of the empirical distribution function. And its limit distribution was calculated by Prokostorov. So this distribution is known as the Charnov distribution. It is the distribution of the argmean of a two-sided standard Brownian motion with a quadratic drift. So that appears as the weak limit of the maximum likelihood estimator. So this was all non-Bayesian work, and I do work on the Bayesian in the Bayesian domain. So usually my papers are about something about the Bayesian procedure for some problem of understudy, like in this context under shape restriction. So if you have to do Bayesian inference under shape restriction, say monotone functions, what you are supposed to do? You put a prior on that is supported on these functions, and then you compute the posterior distribution. Now, if you think about common methods of putting priors on function, so there are several such methods like Gaussian process, a series expansion in a basis. So for example, B-splines is a common basis that is being used. But if you have a shape restriction, so then it imposes cumbersome conditioning on, say, if you are using Gaussian process, it would be a Gaussian process conditioned on that it's increasing. That's really cumbersome. With series, it's a bit better. So with B-spline especially, that's really a nice series when you think about structures, because a B-spline series would be increasing if and only if the coefficients would be in the increasing order. And that just means that you have to put a monotonicity restriction on the coefficients. But still, it's a restriction that is not easy to handle. I mean, it's computationally kind of challenging, but that can be overcome with modern computational techniques like Hamiltonian Monte Carlo. But it's theoretical study that is the real challenging part, and there's no easy answer to this. For the density, there is another approach that can be done, because a decreasing density can be represented as a scale mixture of uniform. So what you can do is you can put a prior on the mixing distribution, which is typically taken a so-called, I mean, if you have seen this called Dirichlet process, that's the very popular prior on distributions. If you have not seen it, that's okay. I mean, it's just some kind of a popular prior distribution on space of distributions. So it's a non-parametric prior. And that works well in the sense that you can derive some properties. So we'll briefly talk about that. Yeah, actually, you can calculate whether how fast that concentrates near the truth. So that kind of result you can do, but there are other properties that you might be interested in. So when we do a Bayesian procedure, I mean, we may be interested in its frequentist aspect. So in repeated sampling, how accurate is the procedure? So just like you ask this for any other procedure, like maximum likelihood or some least square based procedure, you can ask the same thing about the Bayesian procedure, but it's somewhat also not just the estimator, but you want to look at the whole random measure. How does it behave under a frequentist setup? So in particular, we want to know, say, if theta is the parameter and theta 0 is its true value, the first question that one would ask is, does the posterior distribution of theta concentrate near the true value as sample size increases? And if that happens, I mean, we call that property posterior consistency. And if that happens, you want to know how fast will that happen. So that will what we call the contraction rate. If you want to do testing, so you want to know whether a Bayesian test have low size and high power. And finally, and model selection, variable selection. So model selection, you want to test among various different models. You want to pick up the right one, whether the posterior assigns a high probability to the correct model, provided it makes sense. And that's very related. Special case is variable selection in regression type setting, where you want to pick up the active predictors. So that gives you a model, and that corresponding model you want to put very high posterior probability. And then about uncertainty quantification, you want to know what is the frequentist coverage of a Bayesian confidence set, which is commonly known as a credible set, whether that essentially agrees with the posterior probability content, that is the credibility of this. So these results have been coming up from last several years, and it's somewhat more challenging than just finding the how fast the posterior contracts near the truth, because you often have to do some kind of modifications to get a positive result in this context. It's important for several reasons. One reason is, of course, if you want to study it from the frequentist point of view, but then also if you are just a plain frequentist, but you want to use Bayesian method for convenience, then it's really, if you have a positive result like that, then it's really useful, because Bayesian credible sets are easy to find. For example, you can just use sampling-based methods to create that. You don't have to necessarily look at limit distributions and cutoff points and such stuff. So they are easy to obtain, but at the same time, if they are valid from frequentist point of view, then you have a reason to use that. So that's why such results are important. And we would like to study such a result in this context of monotone functions, monotone regression functions. But the way we'll do is not the traditional Bayesian method, but in a different approach. So let's say we have a prior on monotone regression function to be put through, say, step heights of a step function. So step functions are B-splines of degree 1. And in this context, I mean, in an estimation context, when you deal with certain functions, you choose the order of, I mean, the degree of the B-spline. And in this context, degree 1 suffices. In fact, if you go beyond degree 1, there is no particular advantage if you don't assume any smoothness. In fact, it can be counterproductive if you use if you go to higher degrees. So we use step functions, and on step heights, we put priors. So a natural prior on the step heights would be, for example, a normal prior, but then you know that they are increasing, so you have to order them. So you have to restrict this distribution to the order state, or a state of order values. But this order restriction makes the posterior analysis very, very complicated, and to a lesser degree, the computation also. So instead of that, so what is happening in this context is an example of a general situation where the parameter space can be thought of as a subset of a bigger unrestricted space where the model still makes sense. So for example, here, if you disregard the order restriction, it gives you class of functions on which the regression still makes sense. And our interest, if we know that function has to be increasing, then that is the restriction. So that is a part of the parameter space. So whenever you have a situation like that, instead of going in this way, there's another way of doing that. So if you just look at the bigger parameter space, and there, for example, the step heights, they are not restricted. You can use independent normal priors, and that's posterior conjugate. So the posterior is very easy to obtain, and it also easy to theoretically study its behavior because all the expressions are explicit. But the problem is that it does not comply with the order restriction, which we certainly want. So when we want to make inference, we don't want to take this posterior because it doesn't comply with the order restriction. So what we suggest is an offbeat idea. Of course, I mean, it's not being used for the first time, but it has not been well explored. So that's what we are recently promoting. So it's a little bit offbeat idea where what you do is we get this simpler normal conjugacy-based posterior, which is non-compliant, but then we use a correction map to correct it, make it compliant so that it lives in the right space. So for example, it could be a projection map. So that takes these arbitrary functions to monotone functions. So in this context, because everything is stepped, so it's just projection of this coefficient vector. So you get some sample from the posterior and you isotonize it. That's the isotonization operation is the projection, and then it gets an induced posterior measure. So that we can call the projection posterior, and that would be used to make an inference. So what's going on really is, in other words, we are using, I mean, here we are supposed to enforce that, I mean, put that, do this isotonization at the prior stage and then update to a posterior distribution. But here we switch the order of this operation. So enforcing the restriction after we do the posterior updating. So this can be, comparison is like this. The traditional base is like your parameter is theta, you have a structural restriction. So you use a very common prior and then make it a compliant prior by through this map, and then you update. So that's the usual Bayesian posterior. So here what we are doing is we do the updating first, and then this is neat expression, and then we have this compliant mapping. I'll not go into the philosophical discussion of this. So when I gave this foundational talk last year at the ISBA meeting there, I talked a lot about what does it really mean from Bayesian point of view and how much Bayesian is that. So here I would rather look at the analytic properties of this in this particular situation. So we'll start with the univariate situation, and that would be a good starting point because a lot of things would be similar. In the univariate situation, which I did with another student, Momita Chakraborty, who graduated, I think 5 years back, 4 years back, whatever. So there it's like step functions, and we have this independent normal prior. We start with the binning, and this number J, number of bins, that is deterministic. That's good enough for the purpose we are studying. And it should go to infinity at an appropriate speed. Then we draw this sample from the unrestricted conjugate normal posterior, and then we isotonize this weighted by this cell frequencies, how many X observations fall in each cell. And that induced distribution is used to make an inference. And then we discuss the most interesting and challenging property of this, namely coverage of a credible interval. So credible interval here, we specifically look at equal till posterior credible interval. So we have a 1 minus alpha credibility. So we take the quantiles of this posterior distribution. Yes.
Could you elaborate what the map is. So what does it mean to isomerize?
Yeah, so here, so this is arbitrary function, I mean step function. So its projection is the closest monotone function. But it can be also described in terms of the coefficients, and you just need to isotonize the coefficient because the projection is also a step function, which can be mathematically shown. So it can be obtained using this weighted Pava algorithm, for instance. So this is pretty fast, and it can be very easily.
But what? So how does it work? So how do you turn the coefficient? I guess I'm asking about the actual algorithm.
Oh, the algorithm, Pava is a well-known algorithm. What you do is, like, whenever there is a violation, you put them equal and make them the same by averaging. And so this way you iteratively do that, several iterations, and makes it. So that is well known for the maximum likelihood. And here we are just applying it on the posterior context. So it's a Bayesian parallel of that. Okay, so that's how we get the induced measure. And so we get basically the samples, the isotonized samples, and then we have this function that is now isotonized, and we are looking at one point. So we get posterior distribution of the function value at the point, I mean this projection posterior, and then we construct this equal quantile intervals. But then the question is, does its coverage go to 1 minus alpha? Its credibility is 1 minus alpha, posterior probability content. Well, it's not obvious for several reasons that this should be 1 minus alpha, because I mean, these are very different objects, the credibility and coverage. So for example, in the parametric case, it does happen because of the so-called Bernstein-von Mises theorem, but we sort of got spoiled by this theorem. We thought this is something that is supposed to happen, but that's not really the case. So as soon as you go to non-parametric problems, for instance, like smoothing problems, then a famous result by Dennis Cox showed that the coverage of a Bayesian credible region can be arbitrarily low. So, and then one has to do some tricks to modify to make the coverage work. So what happens in this context? So we have a result, we can calculate the asymptotic coverage. So this is the theorem we had with Momita. So here's some notations. So for a function f, let's define a functional. So delta f star to be ft plus t star. You look at the argmin of this. Let W1, W2 be two independent two-sided Brownian motion. C0 be this constant 2b over this, where a is, I mean, this is dependent on the density of the x, and this is the derivative of the function at the point of interest. And Fn hat is the sieve maximum likelihood estimator, so which is like the maximum likelihood estimator, but based on this binning restriction. So then we have this result. So it's not surprising that the limit distribution of the sieve maximum likelihood estimator is exactly like the maximum likelihood estimator, provided your J is neither too small nor too large. And what happens to the Bayesian thing, like the projection posterior distribution? It has a weak limit, and it's given by this. So same constant, but with this delta, the functional is not here W1, but it's W1 plus W2. This are two independent, conditioned on W1. So this is a random variable. So this goes weakly to a random variable, not a constant. Okay, that's natural because it itself is a random measure. And then if you center it, that's what one does with the Bernstein-von Mises theorem using the standard estimator, then it does not have a limit in probability. So it doesn't quite give you immediately this correspondence between Bayesian and Frequentist. Well, so this is a slightly larger J than we need to get for optimal L1 contraction. Now this distribution, delta star W1, is the standard Charnow distribution, but this one is somewhat non-standard thing. So we'll see what this means. So here, to prove this, the key relation is the so-called switch relations. So that characterizes the the estimator, or in this context, the Bayesian analog of that, that's the left derivative of the cumulative. So this greater than something, if and only if you can write down in terms of the unrestricted and not isotonized function minus this. So this process you have to study. And these limits can be studied because we can study the limit of this stuff. So for the CVMLE, this reduces studying the weak limit of local partial sum process. This has a Brownian motion limit. For the posterior, what we have is, there's an additional variation given by a Gaussian process. So that's converging to another independent Brownian motion. And then there are technical verifications of tightness and stochastic continuity. So this can be established from higher order bounds of partial sums of Gaussian process and then martingale maximal inequality. So these are all technical stuff that verifies this corresponding. So the main important thing is for the Bayesian part, there's another independent source of variation. And then you have the conditional, and that gives you that particular structure. The quadratic drift comes from Taylor's expansion, and this has non-stochastic limit. And tightness you have to verify before you apply the argmax functional. So that's how it works. The question is that weak limit anything useful? And we show that yes, it is. So you look at the quantile interval, then this is the quantile. So then this is the key result. This truth belongs to this quantile interval if and only if this happens. And that can be written down in terms of the difference normalized less than equal to 0, right? So if we introduce this notation that this is this quantity, this is the argument function, and C0. So introduce this distribution. This is a conditional distribution function. Then we have this result. So this less than equal to this is this. So and then the limiting coverage of this interval can be written down in this way. So this functional delta star for this plus process, this two independent Brownian motion, conditioned on the first one. So this is a functional of W1. So that is a random, it's clearly a probability, random probability. So it lies between 0 and 1. So this limiting coverage is the probability that this random variable lies between gamma by 2 and 1 minus gamma by 2. Now, if this were uniformly distributed, this would be exactly 1 minus gamma. So then there would be matching. But this distribution is not uniform. It's this distribution. And interestingly, this does not have any unknown parameter. It's a universal distribution. So somehow magically this A and B vanish from the limit. So the limiting probability is dependent on the credibility level, but nothing else. So it's not 1 minus gamma, but it's something that just depends on 1 minus gamma. So we will name this distribution the Bayes-Chernoff distribution because it's connected to Bayesian and it's very much like the Chernoff distribution. There are some differences because Chernoff is on the real line. This is on the unit interval, but it's also symmetric. So the CDF of A is symmetric about half, and it's slightly more concentrated compared to the uniform. So as a result, what that means is that the limiting coverage is slightly higher than the nominal credibility level. So this is opposite of what Cox found for smoothing problems. So for instance, if you're looking for 95% equal tail credible interval, it gives you 96.4 limiting coverage. Well, not bad, actually, it's more. So it's obtained by simulation. But then if you really insist that I want 95%, I don't want 96.4%, then we also have a solution. All you do is you start with a credibility level that is slightly smaller, and you can exactly calculate it. You start with the gamma so that A at gamma over 2 is equal to alpha by 2. Then the limiting coverage will be exactly 1 minus alpha. So for example, to get 95%, you start with 93.2%. Yeah. And simulation showed agreement with theoretical findings. And this procedure is applicable to also monotone density, but then you don't use normal, you use independent normal, you use a Dirichlet prior on because after binning its probability. But then you can do parallel. There are some technical differences, but eventually you get a very similar result. Now coming to the multivariate situation, we'll have a lot of similarity, but there's technically there would be some differences as well. So it's the multivariate version of this regression problem with d-dimensional predictor. A function is called multivariate monotone if fx1 is less than fx2 whenever x1 is less than x2 in the partial order. That means all components are less. Then you have to obey this. So that's the most common notion of multivariate monotonicity. So put a prior. So what we do is we use the binning. So the sales are products, and then we put priors on this random heights. So if you have to ensure monotonicity, you have to look at a prior on this cone, and that's obviously cumbersome. It's more cumbersome than the univariate also. And in this case, the L1 approximation rate is 1 over j with total j to the power j basis function. L2 approximation rate is j power minus f. You can get optimal L1 contraction rate, but that's not the problem we're mostly interested today. So we'll look at the coverage problem. So in this context, we can try to use the same idea, like project this, but it seems that the projection does not give you the optimal contraction rate for function at a point. It's good for L1 or L1 that is global, but not for point-wise. So what do? The projection is more related to distance, and this is not necessarily for the point. It's the L1 or L2 distance may not be the relevant one. So while this natural, the restriction, when we look at this projection-posterior approach, so we use this map to make a correction. So it's natural, but you see, the map being a projection is not necessary for this concept to be used. Some kind of correction map, as long as it works, may be used. So we rather need a map, so iota, that takes from the alternative parameter space, in this case, the unrestricted space of functions, to the target parameter space, that is the monotone function, where so that on the bigger space, the model still makes sense. And a prior on with computable posterior distribution we want, and the random distribution induced by the map has desirable frequentist convergence property. So that is the motivating choice for the map. And we also want this to be computable. So that's also will be coming up as from the choice. So what we do instead of projection for studying the function at a single point, we use this map. So this is the maxibin immersion operation. So it's kind of taking the function values and looking at, so this is the, so over this block, J1 to J2, and then you weighted sum normalized by this, but then you do some kind of operation on it. So you minimize over all bigger than the location. So this is the index corresponding to the point. And so all bigger than this and J1 smaller than this. So you do this operation over all such choices. Now, why is this? Because this is actually motivated from what we know from, thanks to this paper by Han and Zhang. So they showed that, well, by taking simple projection, the maximum, the least square estimator does not have the best kind of property. But if they use this kind of block estimator, that does have this good property for point-wise behavior. So we got that clue from there and then apply with the Bayesian counterpart. And then But there is a difference with their choice and ours. In their choice, it was like more like all continuous blocks. And here we have binned. So we are searching over pairs of integers, and that's a much fewer choice. I mean, much fewer search. So it's somewhat less search, I mean, less intense search because of the binning. But that's a relatively minor difference. In pictorial terms, this is like this. So if you use the projection, it's like, it's also, projection can be interpreted through this bin, through this max bin operation, but then it's not just over those blocks of the squares, but or these rectangles, but over all regions like this. And the max bin is simpler in the sense that it restricts this max bin operation to the blocks of this kind of rectangles only. So that appears to be the right choice. But then, of course, you could have used another one. So first max and then mean. So that is another choice. And both are asymmetric, so you can symmetrize, and this is a symmetric choice. So all these three are sensible choices, and we'll see that all three are useful. So the corresponding immersion for F are denoted by F lower star, F upper star, and F tilde at x0. So in the univariate case, all three operations actually give us the same thing, and that is equal to the L2 projection on monotone functions for stepwise function. It's the standard isotonization of stepwise. But here it's different. So here's the effect of this map on the posterior distribution. So this is like before you do any operation that's based on just the conjugate normal posterior. So it's not very concentrated. This is the correct value. But once you do the operation, it becomes much better behaved. And that's the posterior that we'll be looking at. So to study, we have to make some assumptions, and it's some more or less parallels the non-Bayesian counterpart. So a list of complicated notations. So basically beta k is, every direction there is when the first derivative is non-zero. So that's when that's like how much, how far you have to go when this finally becomes non-flat. Each direction we can look at this. And so for certain direction out of D, S many, they have this, they're this regular, so finitely many steps, and then it's not flat. But then there are some flat ones. And then this is the key assumption that the function has an expansion near the truth. So this is a Taylor type expansion with number of terms coming from this set. So this is like where, so the index that is the in that direction the farthest. So those are the terms that appear, and after that it's a small error. So that's a standard assumption in this context. And for so basically the terms lower than that do not appear, so they just are zero. Okay, so then we can describe the limit distribution as follows. So let H1, H2 be two centered Gaussian processes with covariance kernel given by this. And then you define a new Gaussian process as follows. It's a linear combination of these two Gaussian processes with this, when this being coefficients, and then there's a drift term, this. And then define Z lower star to be sup inf and Z upper star to be inf sup. So it's the sup inf over these blocks. Then the limit of the posterior can be described as follows. For these three different immersion maps, you get the corresponding weak limits, very similar, except that they are given by this Z lower star, Z upper star, and this is given by the average. Not surprising because this was obtained by the averaging of this. So this, for this, you need J case to be bigger than the corresponding rates. Like in the univariate case, we needed to take this bigger than n power 1/3, that's the reciprocal of the rate. But at the same time, not too large, so that is the restriction. So we have plenty of choice within this range, and then you have this, and that leads to, well, we'll see that will lead to some good, that would lead to limiting coverage. But let's look at some special cases. What happens in the univariate case is, in that case, you can write down HIs as in this way. So this is the Brownian motion. So you see, this has two arguments. So this is in the same process in two arguments, v and minus u. Then this simplifies to something like this. So this is coincides with the slope of the greatest convex minorant of the process this. So that's how that its connection with the old one. And then you get the apply the switching relation. That is how you transform this greatest convex minorant, the derivative, to the original process. And that leads back to our old result. So that's nice to recover that from here. But more generally, so under some special situations, so if L, that index set, is like this. So this is like every direction there is just, it just consists of some extreme ones. So if there's no mix, so in each direction, just only one that is the largest and everything else is zero. So this is the unit vector with one and rest zero. So then the U process can be written in this way, some U tilde times a constant, where this U tilde constant is given by this, and U tilde, from U tilde, what disappears is the role of the, here U tilde, you had these things, this ds, blah, blah. So that was, so that thing would disappear and it would be kind of universal thing. So that is the point. So it will not involve the density of the predictor. So this happens under certain situations. For example, if these betas, this index in each direction, these are relatively primes, or in particular if they're all one. So that's the classical, the most common case where in each direction it has some action. So this basically says that it's truly, at that point, it's truly increasing in each direction. So that's like the regular situation. And of course, the univariate case. So in that case, the coverage of credible interval, you can write down as the asymptotic coverage as this probability that this lim sup of this process, sup in of this process, conditioned on this one of the arguments. So this is like that random variable that appears. So this is for that particular ordering of operation, that's ZB1, but ZB2 and the other ZB3, they will appear with the other two type of immersion maps. Okay, so I don't have much time, so not really spending time on proofs. Okay, so let's pass that. So because, if I cannot spend time, it doesn't mean much. So let me show some numerical. This first thing is like the tabulation of this distribution. Now, these distributions are really complicated stuff. So we don't know how to analytically handle them. At least our knowledge of probability is not enough to handle that. So, but these are universal. There's no unknown in it. So we can just simulate this Brownian motions thing or Gaussian with that known kernel. So for different betas, we so this in 2 dimensions. So these are the distribution functions. So what you can do is see is that at 0.7, if this were uniform, this was supposed to be 0.7, but these are somewhat higher, which means there's more concentration in the middle in these distributions. And as a result, the corresponding quantiles, so this gives you the correction table. So if you want to get a 95%, then you have to work, well, actually one has. So one has to read from this a table like this. So that says that you have to start with a lower credibility level, appropriately calculated from this table, so that you end up with the exact limiting coverage. So we'll consider, and then simulation study, we considered some functions that are multivariate monotone, and then normal error, uniform predictor, and different sample sizes. We took J to be slightly bigger than n power 1/3. And then this is the comparison, not, well, you see that this is the coverage, the target should be 90.95, so 95%. So with 200, it's not picking up very well, but from 500, etc., it's more. And then this is the adjusted one, so that's getting close to the target. And this is the correspondence with corresponding non-Bayesian procedure in Han and Zhang. So, okay, so I mean, what we can see is that in terms of length, the Bayesian intervals are a little bit shorter, not a whole big difference, but still some improvement. That's not bad. And this happens more or less for all the functions we studied. So it's kind of boring to go over table, so forget that. So we'll end with some conclusions. So what have we done? So for statistical problems such as function estimation under shape restriction like monotonicity, traditional Bayesian approaches are cumbersome and it's hard to analyze their frequentist properties such as posterior contraction rate and coverage of the credible set. What we demonstrated that by switching the order of two steps, the order restriction and posterior updating, it gives rise to a much more tractable posterior like random measure, which we call the projection posterior, or more generally, which is the distribution of the projection on the space of monotone functions of a sample randomly obtained from the unrestricted posterior distribution of the function. More generally, we used an immersion map that immerses in the right space, randomly obtained from the unrestricted posterior distribution. And we obtained the asymptotic coverage of a credible interval in terms of two independent Gaussian processes. And we found that to be slightly higher than the corresponding nominal credibility level. Then we showed that by a recalibration technique, we can achieve the correct asymptotic frequentist coverage. The difference is minimal, so you can leave it with that, but you can also correct if you want. And the simulation showed validation of our theoretical findings. So that's all. Thank you very much for your attention and coming today.
Does anyone have a question for the speaker press? Yeah.
So thank you for the talk, very interesting. I guess abstracting from the specific problem to the big question of, essentially this, when you apply the constraint, whether you do it before in the prior or you do it period. So a similar idea comes up pretty often, but the motivation is computational, but it's the parameter expansion.
Exactly. I also use this in two other contexts. One is this differential equation models where the function is given, it's a parametric nonlinear regression function is implicitly specified by a differential equation, but it's kind of hard to put a prior of complying with that. So instead of that, we put a non-parametric prior, and then we project on the space of functions, so induced posterior, and that we showed there is a Bernstein-von-Mises theorem. So the parameter, the Bayesian interval will have asymptotically frequentist coverage. And also in the high dimensional context, we can use the project on a sparse subset and can show that posterior has, it's much better computable and it also has desirable properties. Yeah, sure, go ahead.
I guess the kind of setting that I had in mind are, so the difference in, at least in the context in which I use parameter expansion for computation, is that there is a non-identifiability problem in the original model. And so the reason why you're putting the constraints is that in some sense the MLEs are not well defined or not unique, because of the identifiability issue. And so they, for computational purposes, you kind of remove the constraints, you do all the computation in that constraint space, and then you apply the constraint back to the posterior to kind of identify. So I wonder, not necessarily the results on coverage, or maybe the results of coverage, but more broadly the results of consistency, you know, that results, whether that kind of idea can be used in that context when even when the model without the constraint is really an unidentifiable.
Here the problem is, I mean, you have a regression problem, and so you can put a prior without the constraint, and that will give you, I mean, and because it's binned, and that's how we put a prior to receive. So it's still, I mean, it's still something sensible posterior, but then it does not have that kind of concentration because it does not use the real real feature of this model, that is it's monotone or whatever. So that's why with this and the picture I showed, that with this, once you put the operation, then it becomes, the posterior becomes much more concentrated around the truth. And so that is the purpose, but you can actually use that, but it won't be very accurate inference. It would be just very dispersed. The posterior would be very dispersed. But here there's no such identifiability problem because it's non-parametric. So it's just, we're not trying to identify parameters here. It's